So far, we had discussed about single sideband modulation scheme. What is important to know is that single sideband generation is not so trivial, unlike the other modulation schemes. So we'll discuss now about SSB generation. The most intuitive approach of SSB generation would be the filter method, where basically you have the message signal xt, carrier frequency is fc. Let me go back to the SSB ones. Yeah, carrier frequency is fc. You modulate the signal by the carrier frequency, so it shifts around fc, and you use a filter to just keep either the upper sideband or lower sideband. However, as you can see from here, that at the frequency fc with a small transition width, that filter is very difficult to design. So the practical implementations of these filters, which are known as sideband filters, has to be done in multiple stages. Multiple stages means, for example, from the picture given below here, you choose a frequency f1, you modulate the message signal with a carrier at f1. So the signal now at this point is around the center frequency f1. You pass it through a band pass filter at f1, which has a transition of 2 beta, let's say. So 2 beta transition means something of this sort. So you have a band pass filter. So at around, so this is the transition. That means around this cutoff frequency, you have beta to the left and beta to the right. That is the transition. So this is a stop band. This is the pass band. That's why we say this is the transition to beta. And you have a band pass filter 1. So this is at a lower frequency f1. Then you modulate by higher frequency f2. You now can have a transition which is to beta prime, which is where beta prime is much larger than beta. Because now what happens is, see, this portion does not exist. So only this portion exists. And when you shift by another, the higher frequency f2, then the difference between this two, actually you have this and you have the corresponding negative image of this upper sideband, which gets shifted around frequency f2. So the distance between upper and lower sideband now increases. So that's why you can now have a transition of beta prime at f2, and you have the corresponding carrier modulated output. Okay, so f2 is much greater than f1, beta prime is much greater than beta. However, this is typically done in multiple stages, 3-4 stages. So beta, the transition width depends on the spectral hole, and we provide a transition region to beta of the filter. So spectral hole is what we discussed here. For example, for a speech signal, you had a spectral hole because the low frequency close to DC content of a speech signal is not much of a significance. With fixed transition to beta, the center frequency of the filter cannot be increased arbitrarily, as the order of the filter would be extremely large. So modulation is carried out in stages. The architecture is very heavy, as you can see here, due to large number of sideband filters. These are large number of several sideband filters, 3 or 4. And another important problem with this architecture is that you have two different local oscillators which needs to be synchronized. That means they need to be generated from the same source. That means, for example, you have a master oscillator from where you generate f1, and then from the same oscillator you generate f2, maintain the same phase balance, and so on and so forth. So in practice, more than 5 stages are often used, and that means you need more than 5 such oscillators which are generated from the same master oscillator. It's not at all an easy job to design this circuitry. Okay, if it is just 2 stage, we could have done it, but multiple stages. So this is a intuitive way of understanding single sideband concept, not a practical method. So We now move to two practical methods of generation of single sideband. One is known as heartless architecture, which is known as phase shift method or phase shift architecture. The second one is known as Weaver's architecture. And in modern handset, receiver handset, modern transceiver, either you have a Hartley architecture or Weaver architecture based on your, trade-offs, what we will study here. Weaver is more widely used, more modern actually. So Hartley's architecture, let's recall the single sideband, what we studied in last lecture, the time domain representation. If you try to see, let me go back to few slides. Single sideband, we had the time domain representation through this low pass band pass equivalent. We found that it was modulated signal was something of this sort. Half AC, xt cosine omega ct, this is the in phase component, x cap t sine omega ct, this is the quadrature phase component. Xt is my message signal, x cap t was Hilbert transform of my message signal. Okay, we will implement this time domain representation as it is in Hartley's method. So which is AC by 2 xt cosine omega ct and AC by 2 x cap t sine omega ct. Sine omega ct is nothing but cosine with a 90-degree phase shift, minus plus. So you have two double sidebands with quadrature carrier. Okay. Individually, if you see them, this is one double sideband and this is another double sideband. The carrier is a quadrature. The message signal also are Hilbert transform, 90-degree phase shift, xt and x cap t. That's it. So what we'll first do is from xt, we'll generate xt and x cap t. So this is a 90-degree phase shift network. But this is not a 90-degree phase shift network at a particular frequency, which is easy to design. This is a 90-degree phase shift network operating over the whole bandwidth 0 to W, the message signal. So this is wideband 90-degree phase shift network, very challenging to design, not very easy. But if you can, this method is very good. So you have xt, x cap t, and then how do you generate DSB? If you recall, it's very simple, balance modulator. So xt balance modulator, you get AC by 2 xt cosine omega ct. X cap t balance modulator, you get AC by 2 x cap t sine omega ct. The two carriers are quadrature phase shift. So you have a carrier input, which is at a frequency omega c. Pass it through a 90-degree phase shift network, but this is the 90-degree phase shift network only at a particular frequency, FC. This is very easy to do. So basically you have two signals, two carrier signals, which are 90-degree out of phase. So this is used for generating this DSB. The quadrature component is used for generating this DSB. And DSB, if you recall the spectrum, DSB spectrum was you have upper sideband, lower sideband. Here also you have upper sideband, lower sideband, and you combine them. Either you add them to get upper sideband, the lower sideband is out of phase, gets cancelled, or you subtract them to get the lower sideband, one of them, the upper sideband gets subtracted and gets cancelled. So this is a combiner in RF. So DSB sidebands are phased such that they cancel out on one side of FC, add on other side. So this method is also known as an image canceller technique or image cancelling architecture. Whenever you hear these names, Hartley's architecture, phase shift architecture, image cancel architecture, they all actually refer to the same similar methodology. Quadrature phase shift network is ideally unrealizable. It's approximated actually in practice. It's never very challenging to design a wideband quadrature phase shift network. So the approximation imperfection or this, variation over the bandwidth, deviation from the ideal characteristics of a quadrature phase shift network actually reflects in this poor image cancellation. You see, here you have two images, upper, lower, here upper, lower, corresponding phase difference. When you add them, only one remains. When you subtract them, only other events. So this image cancellation is now not fully done. So very accurate balancing is required between these two stages. Well, so in practice, it's difficult to go beyond a 30 dB suppression. So very high quality image suppression you cannot obtain using Hartley architecture unless you concentrate on designing this guy over here. We'll now move to Weaver's architecture. Weaver's architecture would require some more insight into the understanding. Weaver architecture, it has no sharp cutoff filters, neither has wideband 90-degree phase shift network. So whatever two methods we studied, the regular method, intuitive method requires sharper cutoff filters. Heartless architecture would require wideband phase shift network. So Weaver's architecture gets rid of these two stringent requirements. The signal energy is confined to the desired bandwidth. Any unwanted sideband, for example, in this case, unwanted sideband, if you wanted upper sideband in Heartless architecture, the unwanted was in lower sideband. So here, any unwanted sideband, if it is not properly done, would occupy the same band as the desired one. So within the desired band itself, the unwanted sideband would reside, and henceforth you do not actually waste the bandwidth or grab more bandwidth. So consider this kind of input signal spectrum, which has a bandwidth of W. FL is the low frequency. FL plus W is the FH, higher frequency. Center frequency is F0. The bandwidth is W. Okay. Let's say this signal in time domain can be written as combination of several sines and cosines, Fourier analysis. So which is denoted by EI, which is summation n equal to 1 to capital N, En cosine omega nt plus phi n, where each such components of frequency lies between FL and FL plus W. We have a small spectral hole basically between minus FL to plus FL. So let's consider this kind of signal spectrum. So EI, the architecture, Weaver architecture is something like this. EI, you have two frequencies, omega naught and omega c, two oscillators. So 90-degree phase shift at omega naught, this is low frequency. You get cosine and sine. It passes through balance modulator. You get two signals, EA1 and EB1. Omega naught is chosen such that it is we'll see what omega naught is. So EA1 and EB1. You have a low pass filter which filters components only between 0 to W by 2. Output of the low pass filter is EA2 and EB2. This is the first stage. In the second stage, you have this local oscillator omega c passing through a 90-degree phase shift network at that frequency. You have cosine and sine omega ct. You have a balance modulator which has input EA2 and cosine, which gives you EA3. You have the second DSB balance modulator which has an input EB2 and sine, which gives EB3. EA3, EB3 combines together to form the output E0, which is upper sideband, or you can combine negatively, that means subtraction, that is also combining basic process to get the lower sideband. Okay, let's analyze these components, EA1, EB1, EA2, EB2, EA3, EB3, final output E0 to get an idea. So as before, the input signal EI is collection of cosines. Likewise, you can write sines, but I have omitted because if you put a phase shift on 90 degree, you get a sine. So En cosine omega nt plus phi n. EA1, since it's multiplied by omega naught and cosine omega naught, is basically cosine En cosine omega n minus omega naught t plus phi n plus En cosine omega n plus omega naught t plus phi n. EB1, which is multiplied by sine omega naught, is basically En sine omega n minus omega naught, sine and cosine, plus En sine omega naught plus omega n. So one is cosine and cosine gives you cos plus cos. One is sine and cosine gives you sine plus sine. Okay. Now you have the low pass filter over here between 0 to W by 2. And you obtain EA2 and EB2. Okay, let's see. The low pass filter passes between 0 to W by 2. W is the bandwidth of my original signal. Huh? So when it is multiplied by omega naught, what happens is the spectrum gets shifted like this. Huh? So from W by 2 to when it's multiplied by omega naught, the center frequency is omega naught. I was telling what is omega naught that time. You see, center frequency is omega naught. That means original signal was FL to Fi. Fi is FL plus W, and the center frequency is FL plus Fi divided by 2, the center frequency. So the first carrier, local oscillator is at a frequency of omega naught, F naught. It's a low frequency, easy to design. So where does the center frequency shifts when it is multiplied by F naught? It shifts to 2F naught. Whereas this lower band shifts when it's multiplied, it shifts to 2F naught minus W by 2, because you have excursion minus W by 2 and plus W by 2. So between W by 2 to 2F naught minus W by 2, you see, between 0 to FL, there is no signal present. So between W by 2 to 2F naught minus W by 2, you do not have any signal energy present. So due to the absence of signal energy, it actually facilitates that transition. That is my transition width of the low pass filter at the low frequency. Between 2F naught minus W by 2 to infinity, it's a filter stop band. It has the desired attenuation. It's very easy to design. So this filter does not require that sharp cutoff. So FC is the, now we will use the second stage of the Weaver architecture, which is the local oscillator FC. FC is the band center of the desired sideband, single sideband, band center of the desired single sideband. Okay. So after it passes through a low pass filter, what is, you have signals EA2 and EB2. What is EA2? You only keep the low frequency portion. So EA2 is En cosine omega n minus omega naught t. So this gets attenuated. EB2 is En sine omega n minus omega naught t. This gets attenuated. En sine. Very good. So EA2, EB2, after it passes through the second stage balance modulator, you get EA3 and EB3. Carrier frequency now is FC. So FC is the band center of the desired SSB again. So EA3 is, now this multiplied with this, you have EA2 multiplied with cosine. So EA2 multiplied with cosine would give you cos plus cos. So En by 2 cosine omega c plus omega n minus omega naught, and omega c minus omega n minus omega naught. So basically omega c minus omega n plus omega naught and minus phi n. EB3 is what? EB3 is EB2 multiplied by sine. EB2 is this guy multiplied by sine. Sine with sine would give you En by 2 cosine omega c plus omega n minus omega naught t plus phi n, and omega c minus this guy, which so it turns out to omega c minus omega n plus omega naught t minus phi. Let's add them together to get the final output E naught, EA3 and EB3. So if you add them together, EA3 and EB3, what do we get? You see here, this is this term and this term gets cancelled. We are left with omega c plus omega n minus omega naught. En cosine of that plus phi n. Where is the location of this frequency? It's upper sideband. It is as if the carrier frequency, the center frequency of the band we said is FC, center frequency. Carrier frequency as if is omega c minus omega naught. So now if you want as if the carrier frequency is omega c minus omega naught. So where is the location of this band? It is with a center frequency of Fc. It is Fc minus W by 2 to Fc plus W by 2. If you subtract them using the combiner, EA3 minus EB3, what do you get? Cosine cancels. The first set of cosine cancels, this minus plus this. So you have En cosine omega c minus omega n plus omega naught t minus phi n. Where is the location of this? This is the lower side band. Carrier frequency as if it is Fc plus F naught. So correspondingly, you can choose, Fc if you want a different carrier frequency. So for the choice of band center, Fc, if you choose this as Fc, local oscillator, which corresponds to a band, it turns out it is the band center of the side bands of the final modulated carrier, and as if it is it is SSB with a carrier frequency of either Fc minus F naught or Fc plus F naught. Very good. We will understand this from a pictorial point of view in the next slide. So let's see. So spectrum at various points of our Weaver architecture. Very carefully. We have frequency. This is the real and this is the imaginary. I tried to plot it in a 3D plot. So you have to understand it from that point of view. Frequency, real portion, imaginary portion. Imaginary portion is horizontal lying down. Real portion is vertical. The frequency, this is the frequency axis. So now, consider my signal, which is EA1. EA1 is what? The original signal was this chap. This is shifted by omega naught. Omega naught is what? Center frequency of the original spectrum. So when it gets shifted, it shifts to the positive, shifts to the negative. So this shaded portion shifts to the positive, and the dotted portion is basically the original signal shifted to the negative. So there is an overlap here. This gap where it ends here is W by 2. So as you filtered that out, you are left with minus W by 2 to plus W by 2. Only this portion. Okay. So this is my EA2. Now let's see. After EA1 filtering happens and you get EA2. After EA2, the second balance modulator, you get EA3. Let's see what we have. Second balance modulator, EA3. That means it is now shifted by Fc. So this is shifted to the positive and this is shifted to the negative. Note that here things are jumbled together. The sidebands, as we said before, that any unwanted sidebands get mapped to the same side, any unwanted sidebands get mapped to the same bandwidth, 0 to means Fc minus W by 2 to Fc plus W by 2. There is no spillover effect. It's just because of this fact. Here things are jumbled together and restricted only within a bandwidth W. Okay. You see this conversion, the original thing was between, you had FL plus W, FL to FL plus W, corresponding you had a negative spectrum. So total bandwidth was kind of positive, negative was something of the order of 2W. Now, after this, this interesting, very interesting shift and low pass filtering, you have the total negative positive spectrum as W. And then you shift it, the second stage shift, and you have positive is W, negative is W. Okay. So originally, if you shifted this chap, it would have been the negative portion would have shifted, and you would have 2W, double sideband. Okay. So this is the interesting step, the first step, where you actually bring down the total bandwidth to W instead of 2W, including the positive negative stuff. Okay. Now let's see the B components of the signal. EB1. EB1 is basically sine, and because of sine, this 2 multiplied by sine is quadrature. So in complex notation, it's J. So that's why in imaginary. So it's a sine. So this guy sine the original spectrum with a sine multiplication. So basically, this is a sine. Your positive shift, and you have a shift in negative frequency. This is minus W by 2, this is plus W by 2. So after low pass filtering, when you obtain EB2, you have the sine components. This is lying in the horizontal plane. Bandwidth is W from minus W by 2 to plus W by 2. And after performing the second stage quadrature, second stage modulation, balance modulation, you get EB3. This is again multiplied by sine omega c. Okay, so sine, now you have cosine. Okay, so you see this one multiplied by sine would now give you something of this sort. This is shifted by positive frequency, you have here, shifted by negative frequency, you have this again vertical. Shaded portion is on the top, dotted is on the bottom, shaded portion is on the bottom, dotted is on the top, because of the adjustment of phases, so plus minus. When you combine these two together, this one and this one, now what happens is the dotted portion remains and the shaded portion cancels. So dotted portion remains. This is as if upper sideband. You see from here, as if this is shifted and you only keep the upper sideband. The lower sideband would look like this, like this, just a mirror image of this. Okay. When you subtract them together, this and this two, you see here the dotted portion cancels and the shaded portion remains, which the spectrum looks like this now. Okay, and this is as if it is the lower sideband. That means when you shift this and if you do a filter and throw away sideband, it is the negative portion spectrum which is left of the message spectrum which is left. On purposely, we had taken a spectrum which is asymmetric to illustrate this point. You see, the positive portion of the spectrum when it's left, upper sideband, negative portion of the spectrum when it's left is lower side. And if you have incorrect image cancellation due to imbalance in modulation, imbalance in 90-degree phase shift, and so on and so forth, this narrowband should not be a problem, but let's say, or any other problem, any other imbalance, then what happens, any spillover, any cancellation, basically is happening within this Fc minus W to Fc plus W. So that actually interferes, stays within the band of the signal. It does not get spillover. It does not get spillover outside. It does not get spillover outside. It stays within the band of the signal, which just adds to the interference noise or something like that. So I'm not harming the total bandwidth. I'm not wasting my total bandwidth. Okay. So imperfections in phasing balancing do not create unwanted sidebands. Unwanted sidebands actually occupy the same band as desired, except that it is just invalid. SSB is difficult to generate if the baseband signal has no DC null or significant low frequency components, as we have told you before. If it has no DC null, it is a significantly high low frequency component, for example, digital data and so on and so forth. You actually have to do the double sideband. You cannot introduce a carrier, you have to do a suppressed carrier. Okay, in the spectrum. In that case, one solution is, which we'll discuss in next lecture, we can use quadrature amplitude multiplexing to efficiently utilize the bandwidth. This is another method we'll discuss. One can resort to vestigial sideband modulation scheme if one sacrifices a strict bandwidth requirement. That means if you have a significantly low frequency component and you still do not want to use a bandwidth of 2W, basically, which is unnecessary, you can do an intermediate compromise, vestigial sideband, which is actually providing you a bandwidth of W plus something delta, with the advantage that you can have an easy circuitry, easy implementation. which is used in digital data, video data, and so on and so forth. Okay. So with this, actually, we end our discussion on single sideband. We'll discuss about quadrature amplitude modulation scheme in the next lecture. So in summary, what we discussed now is we discussed methods of generation of SSB. One is the filter method, which has to be done in multiple stages. Problem is architecture is heavy, lots of local oscillator synchronization required. Second is the Hartley architecture, which is used in practice, provided we can very good, well design this 90-degree phase shift wideband network. This is in many cases designed in DSP. If you take a look at the Oppenheim Schaffer digital signal processing, discrete time signal processing textbook, you'll see there is a design of Hilbert transformer, and digital implementation means it's pretty much decent. Challenge is much less compared to analog design. But again, there are imperfections. So this provides 35 dB as image suppression. If you want even higher image suppression like 60, 70 dB or 80 dB image suppression, you have to use Weaver architecture, which is used in many receiver modern receiver handsets, which has two stages. The first stage is corresponds to a local oscillator at a frequency of F0. F0 is the band center frequency of the message signal, low frequency. It uses 4 balanced modulator, and it uses two different sets of frequencies, and it uses two oscillators, so two oscillators can be connected, so you can generate the second oscillator from the first. So omega naught, you can choose the second oscillation frequency, which is the center of the modulated band. So from omega naught, you can generate omega C by using multipliers, frequency multipliers. So this is not a very difficult task to do, and they will be synchronized. And you have two 90-degree phase shifters, but they are only at that particular frequency of interest where you are generating the local oscillator. So this is easier to implement. And advantage is that you get, after all this thing, you get a spectrum which is concentrated upper sideband or lower sideband concentrated within W bandwidth. Any unwanted spillover gets mapped there itself, and henceforth there is no spinning over. The unwanted sidebands remain in the original signal remain contained within the original signal bandwidth. So we will now look into cases where signal has significant low frequency components, and you do not want to waste bandwidth by using double sideband modulation. Single sideband won't be very effective in handling such signal. Henceforth, we will move to quadrature amplitude multiplexing in the next lecture where we will discuss. Thank you very much.